I want to look just a little bit more at this general idea of the interior product. Not necessarily we're going to use it for anything, but now that I've introduced it, I want to show you a little bit about it. So here's one very interesting thing about the interior product is that if I've got a P form, I can pair that with a vector, let's say EK to be simple to start out with, and then that's going to be a P minus 1 form, and then I can knock it down another peg with another vector, maybe say EI to be simple. Well, it turns out that if I do it in the opposite order, I just get a minus sign. And roughly that's a reflection of the fact that the wedge product switches when you do a minus sign. But we have to be a little bit careful about proving that. And I'm actually going to show you a couple of proofs of that. One is just a calculation where you have to be careful about the indices. Okay, so good time, if you want to try to work that out yourself, and you just have to be careful about the same kind of thing we did up here, this kind of thing of really explicitly linking these indices with the j's. Okay, but let me show you. I'm just going to pop it in here. Okay, so here's one way to do that, and introducing a nice little notation. Okay, sorry about going up and down like that. So suppose that I matches j sub q, and k, this one, matches j sub r. And let's suppose that it happens to be that the jq appears before the jr, so that I is less than k. Okay, so then in this order, and it's going to be exactly similar. We don't really have to do the case where it's opposite because we're looking at in both orders anyway. So without loss of generality, we can assume that I is less than k. Okay, so let's rock on with that just as an explicit calculation. We know that the I e k eating this guy, we have a formula for that. And in order to simplify the notation a little bit, I'm introducing this nice little hat notation. I wanted to be more explicit about it here than I can with the hat notation, but it's really nice now. It's when you have the hat notation, when I have a sequence of things with dot dot dots, the hat means this is the one that isn't included. So you put in all these ones, the J1 through JP, it's understood what those are, and it says kill the dxk, which is exactly what we discovered was happening with the interior product before. Okay. And minus 1 to the r minus 1, because that was this link, that r measured how many switches did you have to get to put that in the front and let it be eaten, sort of absorbed by the IEK. Now we do the same thing with IEI. It's going to be minus 1 to the q minus 1, and the dxi is going to disappear. Now here's what's really important. Because I was assuming I is less than k, the fact that I've deleted the dxk from this list does not affect this number. The dxi that I'm erasing, or essentially moving to the front and letting get killed, is still in the qth position, even though I killed the dxk already. Now that's going to be different, though, when I do it in the opposite order. Here, I'm going to let the IEI work first. That's going to be minus 1 to the q minus 1 with the dxi deleted. And of course, that's just q because I haven't done anything else to it. But now, when I let IEK act, I'm going to figure out how many switches do I need to do to get this k, the dxk, up to here. Well, this was the thing in the jrth position originally, but now it's in the jr minus 1 position because I've already deleted this guy. That might seem like a sort of a stupid technicality, but it's the whole key to this version of the calculation. So I'm going to be switching it past only r minus 1 things, and so this is an r minus 2. Everything else is the same. It's just the same list of dxj's without the dxi, which dxk, but instead of having minus 1 to the q minus 1 and minus 1 to the r minus 1, the minus 1 to the q minus 1 is the same, but this is a different sign. This is exactly minus of what you'd get if you had a r minus 1. Oops, that's a 1. Okay. So in other words, it's minus of what we had up here. So that says that doing the i's in the opposite order gives you a minus sign. Okay. So now how would you... this is only on basis vectors. We really care about it for all vectors. Okay. So how would you show? What the summary should be that if I do i's with two vectors in opposite orders, I get the opposite sign. Or and this is the most formal way to say it, or in other words, if I take some unsuspecting p form alpha, doesn't matter what the p is, and then I do the i's in different orders, and then I get an opposite sign. Well, this is just linearity. IU IV of alpha, okay, that's going to be, well, first of all, let's show that it doesn't matter what the alpha is, okay. Let's take IEI, IEK, that's hard to say, on alpha, well, that's going to be this operation, and then alpha is going to be a sum of, and I'm not going to put an index down there, I'm just going to describe it, of, you know, things like alpha. It's kind of hideous to write this out. Alphas. Actually, I'm just going to put a question mark here, and then dx question mark wedge dot 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 dx question mark. There's various official ways to do this, but the point is it doesn't matter. This is a sum of coefficients times various combinations of the dx's. Okay. Well, whatever these coefficients are, these are just numbers. These are going to come out. The sum is going to come out. That's what it means to say that the i's are linear. And what we're just going to get is we're going to get the sum of the various alphas, who cares about the bookkeeping, times IEK on the dx's. Whoops, that didn't copy right. There we go. Oh, I see. Oh, I hate it when it does that. This was, well, so this was dx question mark wedge. Sorry about that. Dx question mark. Okay. Sometimes my control key doesn't really engage. Okay. And then control V. Okay. So it's just going to be the sum of these guys, but we know from this explicit calculation that that is just going to change the sign if I change the order. So it's minus of that same thing if I change the order. Oop, that didn't really subscript it. And then I can just repackage it. And that's just going to be minus of this with the order switched. So the simple way to say that is if you've got a condition like this, what we're trying to prove, this switching negative condition, is a linear condition. And because this is linear in alpha, it's going to work. Okay? So that proves that it's true if these happen to be basis vectors. Well, what if they're not basis vectors? What if they're arbitrary vectors? IU, IV alpha. Okay. Well, that's going to be Greek I, of sum UI, EI. And that's a vector, so I'll bold it. And then this is going to be a iota of the same thing, but I'm just going to put in VJ, EJ, all acting on alpha. Okay, so that's just going to be a big double summation over I and J. Oh, actually K. I've been using K here because I've reserved the J's for other purposes. Of exactly these guys. Well, guess what? I can switch the order here and then repackage. So it's the same deal. It's linear in everything. It's a linear condition we're trying to prove. When that's true for the basis vectors, it's going to be true for everything. Okay? And that's just going to repackage up to be IV, IU alpha. So let's just write it down. V and U with a minus sign. Okay. So basically, once we knew this was true for the basis forms, you could just say, by linearity, it's true for everything else. It's a very standard kind of argument. Okay. So one consequence of that is very simple, that if I do IU twice, if I take, let me just explicate this a little clearer. This is IU, and that's supposed to be bold, of IU of alpha. That's supposed to be 0. And one of the really, let me prove that right now, and then we'll talk about the similarity. It's hopefully pretty clear, because I can just use this where U is equal to V. If I look at IU, it's equal to minus itself, because if I just put in V equals U, it's going to be itself. The only thing that's minus itself is 0. And so we really have a very nice condition, which is that if I do the same interior product with the same vector twice, I get 0. I can talk about, I don't have the other display up right now, but if you remember that idea of sticking in vectors one at a time into a P-form, something that's designed to take multiple vectors at once and produce a number, I'm saying, what if I put in the same vector in two different slots? Well, for example, if I'm making a parallelogram, that's going to be a degenerate parallelogram. And so I'm going to get 0. So it's very natural that if I put in the same vector twice, I should be getting 0. But I wanted to emphasize the similarity. D was our really, really important operation. It has to do with derivatives. This is pure algebra here, so there is a real difference. These axioms that I had up here, where were they? Right here. It's a purely algebraic operation, but there are some real similarities. There's some linearity principles, although D is not linear in the same way because it takes derivatives. But they do both obey this kind of product rule. And so it's not ridiculously surprising that they both satisfy this property that if you do it twice, you get 0. Okay. So let me, at the risk of making this a bit too long, I want to show you one more proof. I actually want to show you how you could prove this directly and then show this from that. So first of all, let me suppose that this is true, and I'll show you an alternate proof of this, so this isn't circular, and I want to show that this guy, this negative rule automatically applies, and that comes from linearity. So let's look at the iota sub u plus v. U plus v, and I want to make that bold. And I'm going to take that squared. I know that that operation is 0. And just to make it not too abstract, I'll act on some arbitrary alpha, but that's never going to do anything interesting. Okay. Now that is just do this operate the IUV operation twice. Let me just explicitly write that out. Okay, and in each case, that looks better. I'm going to get a sum. So this is going to be, let me pick up this again, IU of this whole thing plus, by linearity on that outer one, it's going to be IV on that thing as well. I had a little problem with the actually, let's say IV of all this stuff. And then it's kind of like foiling out. When I have just two things that are linear, I'm going to get a sort of a distributive law. And so what I'm going to get is IU, and then let's turn this into an IV, alpha, plus, and then now I can just copy it and just modify it. Okay. Plus IU alpha. Actually, I should have made the U first. That makes more sense. IU, IV, IU. Listening to myself, it sounds like I'm not speaking English anymore. And what do we know? Okay, we're assuming that anytime you do the same vector twice, it gives you 0. So that's equal to those are equal to 0. And so it says the sum of IU, IV alpha and IV, IU alpha is equal to 0. Well, guess what that says? That says that they're equal and opposite, the opposite sign. Okay, and so this, just moving one of them over, is the negative of this guy. Very, very common thing that when I have an operation that's linear and it squares 0, it has to be antisymmetric. So that if I do it in opposite order, I get a negative sign. So, but is there a proof that this is 0 that doesn't rely on this kind of antisymmetry in the first place? Well, there is. It goes back, sorry to be confusing about my scrolling here, it goes back to this one. This provides a very nice inductive proof that if I do IU squared is equal to 0. So let me pick that up. Speaking of confusing scrolling, I'm going to pick that up from right down here. And I'm going to show you that argument. Not yet. There we go. Okay. So here's what we're going to assume. We're going to assume that for, let's say, up through P forms, that IU squared on a form is 0, and we want to show it's true for P plus 1 forms, and eventually all forms. So inductively, we're going to do this. So we're going to assume that we've already proved that IU squared is 0 on small degree forms. Well, what about the base case? Well, IU squared on a 0 form is certainly 0. On a 1 form, it's certainly 0, and on a 2 form, it's not too hard to show it's 0, but that's certainly enough for a base case. The reason IU squared on a 1 form is 0 is it would create a -1 degree form. Those don't exist. Those are 0. Okay, so here's what we do. IU squared on a wedge product, we just expand it out. We expand out this inner one using the product rule, the analog of the product rule. Now we just use linearity, and we expand out the outer one with the analog of the product rule. Now we have to be very careful with signs, though. On this first term, I haven't switched the IU past anything, so there's no sign. On the second term, I'm acting with IU on this one, and I'm switching an IU past this form. Well, this used to have degree alpha, but now it has degree of alpha -1. So that's why I'm getting a -1 to this guy, because that's the degree of IU alpha. And that's what I'm switching the operator IU past to get it to attack beta. Now, what about the other two terms? They come from here. Well, there's the -1 to the degree alpha, which is fine. That's already there. And then IU attacks the first thing with no extra sign. Then I'm going to take IU past alpha. So I've taken the original IU past alpha. That gives me -1 to the degree of alpha. And I'm passing another IU past alpha again, so I'm getting -1 to the 2 degree alpha, which, you know what, that's actually just always going to be plus, so you can just delete it. And it's alpha IU beta. Now here's where I use the inductive hypothesis. I have assumed that for low degree forms, say the degree that alpha and beta have, that IU squared is already 0. So let's assume that these guys die, and we just want to show that something of higher degree created by wedging these guys together we don't know if that's 0, and that's what we want to show. So let's look at what we've got. This -1 to the degree alpha -1 is really key, because I can rewrite that as -1 to the degree alpha. And I get IU alpha wedge IU beta, and look what I've got. I've got IU alpha wedge IU beta here. They have exactly opposite signs, and so they die, and it's 0. So that gives you an inductive proof that IU squared is 0 in anything. And then this cute little proof, well, I don't want to call it clever, I certainly didn't come up with it, shows you that you get the antisymmetry as well. Okay. So one more thing about the interior product, and then the next video we'll go back to E&M, electricity and magnetism. I wanted to make a connection. We've introduced a lot of terminology here in these 30 videos or 31 videos. And one of these, there's the tilde. Remember that? Took a vector, or a vector field really, and created a one form out of it. In a very natural way, but that actually has to do with the dot product of space. And then the star, that had to do with the dot product on forms, and that took a 1 form and produced an n-1 form. Well, I've now got a new way to create an n-1 form. Take dv, just dx, just the product of all the dx's in Rn, and take the interior product of that with u. That's going to demote it to being an n-1 form. And I claim that that's exactly going to equal to star u tilde. That is kind of interesting, because this operator has nothing to do with the dot product. Nothing whatsoever. Its axioms just had to do with linearity and pairing forms and vectors, which doesn't have to do with the dot product, and then this nice product rule kind of thing. So it turns out to be very, very, very important and interesting when you go further with this stuff. What of these operations depend on the dot product? What don't? What depends on geometry, and what just kind of depends on topology? Well, the u tilde depends on the dot product, turns out. I think I've mentioned that before. The star, I really was explicit about how it depends on the dot product. Turns out when you combine the two, you get something that's actually independent of the dot product. And so in a way, it's more natural, in a very precise sense of the word natural, actually. So let's just do that real quick. IU dv, okay, that's going to be the sum of I sub ui ei, and that's a vector, of dv. Okay, well, let's write that out. That's dx, and I don't know, what do I want? Let's start it with 1s, because I want the numbers to match up. It really doesn't matter what the indices are. So dot 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 wedge dxn. Okay, doesn't have anything to do with whether we started with 0 or if you have some sign switches or whatever. Okay, and I'm going to do the case without the sign switch, and you can think about the fact that the sign switches cancel out on the right-hand side. Okay, so that's going to be the sum of, I guess over I just didn't put it in before, of the coefficients u sub I. And then what am I getting? I'm getting IUI on the volume form. Well, that's just going to be dx1 wedge dot dot dot, and I'm going to use the hat notation in a minute here. dxn, and oh, I need a wedge right there too. Wedge. Okay. And then this is going to be hatted. I think I have a hat ready to go. Okay. Okay, so I claim that's the same thing as star of u tilde. Because what was u tilde? It was, let's just calculate the other side. U tilde, just this guy, was defined by take the components, the ui's, and just pair them with the dxi's. This is the one. This is something where if we do have a special component in space-time with the funny sign switch, you would get a different sign for the dx naught component. Okay. Well, what about star u tilde? What was the rule for that? It was take any dxi and replace it with, guess what? Exactly this guy. Oh, and sorry, this was a -1. Wonder if you noticed that I just completely forgot that. This is I minus 1. And star u tilde is this summation with these everything else but the dxi. Put a little space in here and here. And what was the sign? It was exactly the sign required to get the dxi to fit in. Now in space-time, there was again an additional sign if this was an x naught, but that cancels out the weird sign from the u tilde. Okay, so it turns out, even though the tilde is very, very important and the star is a very important operator, if you're going to turn a vector field into an n-1 form, there is a way to do it, namely this operation, that doesn't have anything to do with the dot product and the geometry, lengths and angles, stuff like that. That can be very important because it's n-1 forms where if you do d on those guys, for example, then you're doing something like the divergence. So a consequence, I won't go further right now because I don't have it set up, is that the divergence of a vector field only has to do with the concept of volume. You do need the dv, not length or angle or anything like that. Whereas a lot of other operations you do with vector fields really do have to do with the geometry of lengths and angles. Okay, good place to stop this one.